In 1963, the United States poured nearly 5 million cubic yards of concrete into a desert canyon on the Colorado River, 710 feet tall. The result was Glen Canyon Dam, the fourth tallest dam in America, holding back one of the largest reservoirs on the continent and the control point for the entire lower half of the Colorado River. 60 years later, the reservoir behind it has dropped to a quarter full, and engineers have found two problems with the dam itself that almost nobody is talking about. One of them they're patching, the other one you can't patch. And the water for 27 million people has to pass straight through it. In November 1922, 7 men sat down in Santa Fe and divided the Colorado River. Based on flow measurements from an unusually wet stretch of the river's history, they assumed it delivered roughly 16.4 million acre-feet of water per year. They allocated 15 million of it, 7 states, 2 basins, a treaty obligation to Mexico. The problem? The measurements were wrong. Tree ring studies going back 5 centuries, confirmed through Congressional Research Service data, showed the river's actual long-term average is closer to 13 to 15 million acre-feet. Since 2000, the 20-year running average has dropped below 13 million. The compact allocated 20 to 30% more water than the river has reliably delivered over the long term. That error was baked into a legal document in 1922 and has been compounding ever since. Congress authorized the Colorado River Storage Project in 1956 to solve the problem the compact created. Upper basin states needed somewhere to store water so they could meet their delivery obligations to the lower basin, even in dry years. Glen Canyon Dam was the centerpiece. The site was so remote, the Bureau of Reclamation had to build a road, a bridge, an airstrip, and an entire town just to reach the canyon. The town was Page, Arizona, a place that existed nowhere before 1957 except on a Bureau engineer's drawing. On October 15, 1956, President Eisenhower pressed a telegraph key in Washington and set off the first explosion in Glen Canyon. Workers placed that concrete around the clock, the last of more than 400,000 buckets poured on September 13, 1963. The finished dam stretched 1,560 feet across the canyon, enough concrete to pave a 2-lane highway from New York to San Francisco. The engineering architecture matters. Glen Canyon Dam has 3 separate systems for releasing water downstream, each operating at a different lake elevation. At the top, spillway tunnels, emergency overflow only, activated at full pool, used only in rare emergencies. In the middle, penstocks, 8 turbine intakes that generate 1,320 megawatts of power and regulate the river's daily flow. This is how the dam operates under normal conditions. At the base, the river outlet works, 4 steel backup pipes 8 feet in diameter near the dam's floor, built for maintenance windows and short-term experiments, not for running the river alone. You need to understand that 3-tier architecture before you can understand what happened next. June 6, 1983. Record snowmelt sends unprecedented inflows toward a reservoir already near full. For the first time under a real flood, operators are forced to open the spillway tunnels. Then they hear it, a low rumble from inside the left tunnel. They close the gate, lower inspection crews on ropes, and find a hole roughly 35 feet deep, 50 feet wide, and more than 130 feet long. Cavitation had chewed straight through 3 feet of reinforced concrete and into the sandstone beneath. Cavitation. Water moving at extreme velocity creates air bubbles that collapse with enough force to tear through reinforced concrete 3 feet thick. The assumption built into the original design was straightforward. A well-maintained reservoir should almost never spill, and only for very short periods. Nobody had engineered for the spring when that assumption stopped being true. The spillways were rebuilt with new air slot technology. The crisis passed. But 1983 revealed something fundamental about Glen Canyon Dam that would take 40 more years to become a national emergency. The dam was engineered for a world it could control. When the conditions it was built for stopped being reliable, the architecture it was built with became a liability. Glen Canyon Dam was engineered for a Goldilocks world. The reservoir was supposed to stay comfortably full, high enough to run the turbines, low enough that the emergency spillways stayed shut. The outlet works at the base, those 4 backup pipes, were built for maintenance windows and short experiments, never to run the river alone. That world is gone. Lake Powell reached full pool, 3,700 feet, exactly once, in 1980. It took 17 years to fill. Today it sits around 3,527 feet, roughly a quarter of its designed capacity. The reasons for that decline belong to a separate conversation. What matters for the engineering is a single number, 3,490 feet. Below 3,490, water can no longer reach the penstocks, the turbine intakes. The turbines shut down, and the only way left to move water through the dam is those 4 backup pipes at the base. One more dry year puts the dam at the threshold. April 2023. The Bureau runs a controlled 72-hour test through the river outlet works. Purpose? Flush sediment downstream to rebuild Grand Canyon beaches. A standard high-flow experiment. When engineers inspect the pipes afterward, they find cavitation damage, the same process that destroyed the spillway tunnels in 1983, this time attacking the backup pipes at a reservoir level still well above the danger threshold. The pipes were eroding from the inside. A Bureau of Reclamation technical memo from March 2024 states it plainly. In the various Glen Canyon Dam references cited, there is nothing to indicate the river outlet works were intended for long-term water conveyance use at low reservoir water levels. The same memo warns against relying on those pipes as the sole means of sustained releases from the dam. Read that again. The only backup system for releasing water downstream when the turbines shut down was never designed to be the only system, and it is already damaged. The Bureau's response? An $8.9 million contract to reline the pipes with epoxy, completed ahead of schedule in June 2025. But the Bureau's own engineers confirm, relining addresses the coating, it does not fix cavitation. The mechanism that caused the damage is still there, waiting for the next time the reservoir drops low enough to trigger it. Wayne Pullen, the Bureau's Upper Colorado Basin Regional Director. Things are happening in parallel and not in sequence. We're going to be doing everything all at once. That's the first flaw. But there's a second one almost nobody mentions because the first flaw at least has the fix on paper. This one doesn't. The river outlet works sit at elevation 3,370 feet. Below that line, no water can exit the dam through any opening. The engineers who built Glen Canyon Dam in 1963 never installed a low-level drain because they never imagined the reservoir would fall this far. But there is more dam below that line, another 240 feet of concrete before the old riverbed. At Deadpool, approximately 1.7 million acre-feet of water, a reservoir still stretching 100 miles upstream becomes permanently trapped. The water sits stagnant, heating in the desert sun, prone to toxic algal blooms and anoxia, while the people downstream get nothing. You can repair a damaged pipe. You cannot add a drain to a 710-foot concrete dam without essentially rebuilding it. Page, Arizona exists because of Glen Canyon Dam. Its economy, its 7,500 residents, its reason for being all trace back to the reservoir. Marinas like Waweep have extended ramps and relocated docks again and again as the water pulls away from them. Widen the frame? Those 27 million people downstream in Arizona, Nevada, California, and Mexico depend on water released through this dam. Las Vegas, Phoenix, the Imperial Valley, which produces roughly 2/3 of the nation's winter vegetables, the Navajo Nation, and the Gila River Indian community, whose water rights are explicitly tied to the dam's release capacity. In a March 2026 letter to Interior Secretary Doug Burgum, Gila River Indian Community Governor Stephen Rowe Lewis put it directly, the United States must take action to fix Glen Canyon Dam. The 2007 interim guidelines governing how water is released from Lake Powell expire at the end of 2026. 7 states, the federal government, Mexico, and tribal nations need a replacement agreement. They do not have one. Upper basin states refuse to absorb cuts for a crisis they argue they didn't create. Lower basin states hold the most politically powerful agricultural operations on the continent. The Bureau's own draft environmental impact statement for post-2026 operations does not include dam modification options, despite 3 lower basin states writing to Interior that this emission violates federal law. No formal response. The Bureau has procrastinated solving Glen Canyon Dam's plumbing problems long enough, said Kyle Roerink, Executive Director of the Great Basin Water Network. He argues the fix has to be part of the current guideline process, not pushed to some later one. And here's the part that earns this video's title. Experts and a handful of journalists have flagged all of this. What's missing is action and public awareness. The Bureau's own plan for life after 2026 leaves the dam's infrastructure problem out entirely, and most Americans have never heard the words river outlet works. The people who should be acting aren't. The public who should be demanding it don't know it exists. 3 options for modifying Glen Canyon Dam have been studied and modelled. The Bureau is expected to release an appraisal study assessing them at the end of 2026 or in early 2027. New low-level outlet tunnels. Drill new passages through the canyon walls at or near river level, bypassing the damaged pipes and allowing water to flow even at dead pool. Cost? Hundreds of millions to potentially several $1 billion, comparable to the more than $1 billion Folsom Dam rehabilitation. Timeline? 5 to 10 years minimum from authorization to operation. Penstock extension. Lower the existing turbine intakes to operate at reduced reservoir elevations. Addresses power generation. Doesn't solve the water delivery problem below dead pool. Full re-engineering. Allow the river to pass through or around the structure entirely. Supported by some engineers and groups including the Glen Canyon Institute. Opposed politically, years from any decision. Former Bureau engineer Dave Wegner, who spent 2 decades working on the dam, has been direct. If that fails, you have a catastrophe. Every option requires congressional authorization, environmental review, and appropriations. The most optimistic timeline for anything to be operational runs into the early 2030s. The reservoir is closing on minimum power pool now. There are 2 versions of Glen Canyon Dam, and both are true at the same time. Version 1, a fully intact concrete arch, generating power, releasing water, no structural failure. The Bureau has stated the dam faces no structural risk. The pipes were relined, operations continue. Version 2, the same dam roughly 37 feet above the shutdown threshold, with backup pipes that were never designed for sustained use, a second gap below 3,370 feet that has no funded solution, and an agency studying infrastructure modifications on a timeline that ends years after the crisis window opens. Glen Canyon Dam was built for a Goldilocks world, a river that would always deliver enough, a reservoir that would never drop too low, a legal framework built on the wettest stretch in centuries of reconstructed hydrology. That world is gone. The people responsible for replacing its infrastructure are working on a timeline the conditions will not wait for. The 2007 guidelines expire this year. The modification studies published this year or next. The reservoir is less than 40 feet above the line. 7 states, 27 million people. A 60-year-old dam built for a world that no longer exists. The question isn't whether Glen Canyon Dam will reach its limits. The Bureau's own projections say it will. The question is whether the people responsible for fixing it can move faster than the water is leaving. That has never happened before. The fix takes 10 years. The water might not give us 2. So here's the real question. Do you keep studying, or do you start building before you've got the perfect plan? Share in the comments. Thanks for watching it, and subscribe for more Megabuild stories.